welcome to lecture, and grab yourself a pen and a piece of paper. We're going to talk about pedigrees. Okay, our topic for today is pedigrees. Which, as soon as I hear that, I immediately think about dog food, which kind of works because we use pedigrees to follow family lineages, and we most often use them on humans or dogs or horses, something that is bred intentionally and you want to know who its ancestors were. Fun fact, pedigree comes from a French word. Pen is pooping out. The French word is, I guess it's a couple words, but it's Pedigrees. So forgive my French, I don't know how to speak it. But the interesting thing to me is that this means crane's foot. A crane is a type of bird, and its footprint kind of looks like there's a long toe and there's two short toes on each side, and there's a little pad in the middle, and then there's like a tiny little dot to the side where its little back toe touches. And when we draw pedigrees, they can be drawn in this kind of trident shape, or we often end up drawing them in a flat T shape. And so that's where the name came from, was this overall shape reminded somebody of a footprint of a crane, and that's just cool. So let's talk about pedigrees just a little bit. You read in your textbook that we represent pedigrees with symbols. So a square is going to be a male, and a circle is going to be a female. When your square or your circle is not filled in, that means that there is no trait. The trait's not noticed in these people. When your square or circle is filled in, and I'm going to just stripe mine because that's easier, that means that the male has the trait, or a female has the trait. So I'm abbreviating with just W/. Now, we say trait often when we're using pedigrees to talk about humans, we're tracking disorders. So you may see that a filled-in circle or a filled-in square means that the person is sick. That's true sometimes, but other times we're just looking at traits like fur color or horse breed, whatever it is that you're thinking about. So it's not always a bad thing, which is why I didn't write that they're sick here. Now there's a couple different types of pedigrees, and this was talked about in your textbook, but just a little bit, and I want to expand upon it. The first type of pedigree is going to be a pedigree of a dominant trait. So pedigrees of dominant traits. In your book, you read about fur color in dogs, right? So there was the TYRP1 gene, which very uncreative name, but I just kind of get with it. It's the Terp gene. So in the Terp gene, there were two alleles. There was big B equals black fur, and then there was little b equals brown fur, and they follow regular dominance. So big B, or big B would be a black furred dog, and little b would be a brown fur dog. So these are the alleles. This is the gene. And these are the genotypes, which means the black fur or the brown fur, that is the phenotype. Phenotype. Cool, so we've got all of our vocab set up. Now let's make a pedigree. Let's say that we have a male dog, and this male dog has black fur. Now we're filling it in because we're looking at the dominant trait. So if it's filled in this case, that means that your dog has black fur. So I'm going to put a square next to black and fill it in. Brown fur would be unfilled in. This male dog and this female dog are going to have puppies. Very adorable. Let's say they have a litter of 4 puppies. So I've crossed them together. This means that this female and this male are going to reproduce. And this line dropping down is showing you their children in the next generation that I'll draw in a second. Now I didn't fill in this circle. That means that the female has what color fur? She has brown fur. Let's say that they have 2 male pups. Come on, Pin. Here we go. And 2 female pups. And one of those males has black fur and one of those females has black fur. So now that I have the phenotypes indicated, I can figure out the genotype. I know the genotype of mom already. Because she's not filled in, she doesn't have the dominant trait. And if she doesn't have the dominant trait, there's only one genotype available for her. So mom has the genotype little b because she's got brown fur. Dad over here, dad is filled in. We're looking at the dominant trait. So this dad has black fur. The dad has the genotype big B, or big B, little b. We know that dad has at least one big B because that's what gave us the black fur. That's going to be true for these pups as well. They have one big B from their dad. We know that mom only has little b's, so she can only pass on a little b to all of these puppies. So each of these puppies is going to get a little b from mom. And now we need to figure out, is dad homozygous dominant or is dad heterozygous? And the answer is dad has to be heterozygous, has to have a little b because he passed on that little b to these 2 puppies with brown fur. Awesome. Now what would happen if dad was homozygous dominant? So what if dad was big B, big B? That would mean that here's mom, here's dad. Do a quick Punnett square. That means 100% of the puppies would have black fur. So I know that can't be the case here because we had 2 puppies with brown fur. Okay, that was fun, but let's make more puppies. Everyone loves puppies. So here, we'll take this black-furred male, and we will mate this black-furred male with another brown-furred female. They're going to have 4 puppies again. Let's say 2 of those puppies are female. And let's say 2 of those puppies are male. Now they totally could be all female or all male. We're just doing it half-half to make it easier on ourselves. And let's say that both of these female puppies have black fur and both of those male puppies have brown fur. So based on this, I already know the genotype of this mom here, this brown-furred female. Because she doesn't have black fur, she has to be homozygous recessive. Each of these male puppies also has brown fur, so they additionally have to be homozygous recessive. They got this little B from mom, and they got this little B from dad. These two girl puppies, they have black fur, so they must have the dominant trait. Remember, we're following the dominant trait in this family. And then their second allele came from mom, but mom only had little b's. So both of these puppies have to be heterozygous. Something to note when you're looking at pedigrees of dominant traits, it shows up in every generation. So there's no skipping generations. You've got black fur in every single generation. Also, when you're looking at a dominant trait, if the child has a trait, the parent, one of the two of them, also has to have the trait. So if a child has black fur, that means that one of the parents must have also have had black fur. So if I just was given a random puppy with black fur, I could tell you pretty sure at least one, maybe both of the parents also had black fur. And another thing to note, males and females are equally affected by the trait. That's a U. So it doesn't affect males more or females more. So that is our dominant trait. Let's do it again, but now let's look at a recessive trait. So pedigrees for recessive traits. In your book, you read about the black, chocolate, and yellow labs. So the gene for that was MCR1. That's the gene. There were two alleles, the big E, which is going to be color, either black or brown, and the little e, which meant no pigment, no color, which to our eyes looks like yellow, hence the yellow lab. There's a couple different genotypes that can result in this. You can have a heterozygous individual or a homozygous and dominant individual, and both of those are going to have fur color. This one would have been black or brown fur. So they have a fur color. Then if you are little e, you're homozygous recessive, you have yellow fur color. So, which one of these things was the gene? MCR1's the gene. Which one of these was the genotype? Homozygous dominant, homozygous recessive, or heterozygous, those are your genotype options. The alleles were what? The alleles for color or no color, so big E or little e. And then what was the phenotype? The phenotype is black fur, brown fur, or yellow fur. Let's make ourselves a pedigree. So in this case, we're going to be looking at the recessive trait. So now, if you're filled in, you have yellow fur. And if you are not filled in, you have black or brown fur. So it's the opposite of last time because we're filling in the trait that's recessive. Can you see? Yeah. Cool. Lovely. So now let's take a male with black fur or brown fur and a female with black fur or brown fur, and they're going to produce a litter of 4 puppies, a female, a male, a female, and a male. So 4 puppies. And of those 4 puppies, one of them is going to have yellow fur. So now our mystery is, we have the phenotypes, what are the genotypes? We know the genotype for a yellow-furred puppy. So this little puppy here is going to have homozygous recessive genotype. Now because this little puppy has 2 little e's, and it gets 1 from each parent, I know that each of my parents must have a copy of the little e allele. Because otherwise, it would be impossible to make this yellow lab puppy. But my parents have black or brown fur, so that means that my parents are expressing the dominant phenotype. So each of my parents must be heterozygous for the MCR1 gene. I know something else about my siblings to this puppy. All of the siblings to this puppy have black or brown fur, so they must also have the dominant allele for the MCR1 gene. Now, this puppy could have gotten the big E from the other parent, or the little e from the other parent. So I really don't know what the second allele is. The same for this puppy over here and this puppy over here. They all could be dominant, homozygous dominant, or they could be heterozygous. Either way, to us, it's going to look the same. And we won't know until they breed. So let's take this puppy over here. We're going to breed this puppy over here with a female who has black or brown fur. And this female and this male are going to produce 4 offspring. And of those 4 offspring, we'll just make 2 girls. And we'll make 2 boys. What do we know about mom? We know that she has black or brown fur, so she must also have a big E. What do we know about all the babies? They all have black or brown fur, so they must also have a big E. And we still really can't tell who is homozygous dominant and who is heterozygous. Like, we really don't know still. Unless, let's say we take this male puppy and we cross it with another black or brown female, and they produce 4 offspring. 2 girl puppies, 2 boy puppies, and let's say this daughter here has yellow fur. That's enough to help us fill in the genotype for everyone else in the family. Because having this yellow lab puppy means that both my parents have to have a little e. I know mom is big E, little e because she's not expressing the recessive phenotype, but she passed on a little e to this puppy here. And because dad has the little e allele as well, that means that at least one of his parents had a little e. Let's say that it is dad, and dad got it from one of these 2 parents. So it could have been mom. One of the 2 of these is going to have a heterozygous genotype. So we don't know everybody's genotype, but it did help us fill in the genotype of dad here in the 1, 2, 3 generation. So that's pretty exciting. We also could use a Punnett square to try and figure out the genotypes of these two parents. If both of our parents, so if both parents were heterozygous genotypes, then we would expect the ratio of puppies to be big E, big E, big E, little e, big E, little e, little e, little e. We would expect about 25% of the offspring to be little e, little e. And if either one of these parents were actually homozygous dominant, even if the other one was still heterozygous, we would expect 100% of these cute little puppies to be expressing black or brown fur. So 0% EE. Since over here, our little puppies had no recessive, it's likely that maybe mom was a homozygous dominant female. Fabulous. So things to note. 1, in this situation, when we're looking at recessive traits, our traits skipped a generation. So there was no yellow labs in this generation, but they produce yellow lab offspring. So this can skip generations. That's pretty cool. Another thing to notice is last time we said that if a child has a trait, the parents also have to have the trait, and that's not true. So here we had black or brown parents, and they produced a yellow lab. So that means that a parent without the trait can produce a child with it. So that's neat. In fact, that's the indicator to me that it is a pedigree for a recessive trait. If I ever see a male and a female that are unaffected and they produce any offspring that is affected, I immediately think it's recessive because the parents didn't have it, but the children did. Lovely. And then, last thing, males and females. So here it was a male and here it's a female. They're affected equally. It doesn't only affect the boys or only affect the girls. So that's our pedigree for recessive traits. Our last one is going to be a pedigree for sex-linked traits. So we say sex-linked, and when we say sex-linked, we're referring to the sex chromosomes X and Y. Mostly, when it's a sex-linked trait, it's on the X chromosome. So it's often referred to as X-linked, an X-linked trait. The reason it's mostly on the X chromosome is because the X chromosome is just so much larger than the Y chromosome. The Y chromosome itself is pretty, physically it's just smaller, so there's less genes on it. The example we're going to look at for sex-linked trait is something that happens in humans. It is red and green colorblindness. Red and green colorblindness, and there are 2 alleles. There's going to be the big B and the little b, and they show dominant and recessive patterns. So big B is going to be no colorblind, I'm going to abbreviate it CB. And little b is going to be, yes, colorblind. Now, we talked about this being a sex-linked trait, which is really interesting. That means that we can't just use these alleles alone. They have to be attached to the X chromosome. So we have 4 to 5 options for each individual. You can be a XY individual, in which we call you male. Remember, sex has nothing to do with gender identity. And this binary is totally artificial because we know that you could be XXY or you could be XYY. But for talking about genetics, we try and simplify it. So XY is considered a male. Again, all the caveats are there. And if you are a male, the trait for colorblindness is on the X chromosome. So if you are a male that is not colorblind, come on, pen, this is your genotype. If you are a male that is colorblind, this is your genotype. So this is a colorblind male. There's nothing written next to the Y. And that's like the hardest part about these problems, is you always want to make the Y have something, but the Y doesn't have anything because this allele is linked to the X chromosome. So our gene is for colorblindness. These are 2 alleles. It has to be on the X chromosome only. Now we say that females have 2 X chromosomes, and that means that females are going to get the allele on each of those X chromosomes. If you are homozygous dominant, so homozygous dominant female, you are not colorblind. If you are heterozygous, oh no, now you have the allele for colorblindness. But because it shows dominance, this big B covers up this little b, and you do not express the phenotype of colorblindness. So your genotype is that you are heterozygous for both alleles, but your phenotype is you are not colorblind, and we call you female here. So that means to be a colorblind female, you need to have 2 of the colorblind allele on both of the X chromosomes. Have you ever done a colorblindness test before? All right, so this is on my computer screen now, and you are looking at the Ishihara Colorblindness Test. And each one of these circles has a bunch of color dots in them, and then there's contrasting color dots in the middle. So in this one stands out really well for me. I can see that there's gray all around it, and then inside there's like a yellow or an orange number 16. This one up here is orange on the outside, and then there's a green squiggly line going through the center. So the contrasting colors help you determine if you're red-green colorblind or green-blue colorblind. There's many different types of colorblindness. And it's called Ishihara because it was invented by a Japanese ophthalmologist and surgeon and teacher, and he invented it in 1918. And he used to paint these by hand with watercolor, and so the originals are really beautiful. Please don't let this diagnose you with colorblindness. Go to an eye doctor for that. All right, so this is what we had before we looked at the Ishihara test. And I've cut my paper in half so I can just kind of like shimmy this upward. All right, now let's look at sex-linked traits in a pedigree, which is our goal for this. So let's take a not colorblind female. Oh no, my pin finally pooped out. Okay. A not colorblind female and a not colorblind male. And they're going to have 4 kids. They're going to have 2 girls, 2 boys, and one of their sons is going to be colorblind. So already I know the genotype of most everybody in this family. Not everybody, but most everybody. And I definitely know this son's genotype because he is a colorblind male. I know he's colorblind because the square has been filled in. So his genotype must have the colorblind allele on his X chromosome. And then since it's a male, he's going to have a Y chromosome. Now that tells me something about Dad. So Dad has a Y chromosome as well. That's what he passed on to his sons. In fact, it's only the sperm that can make a kid female or male genetically, because your mom, she does not ever have a Y to pass on in her eggs. So the sperm is where you get the X or Y chromosome from, that makes a difference, and so your Y chromosome has to come from Dad. So Dad is not colorblind. His X chromosome has a big B on it. And this son's brother is also not colorblind, so he has the big B and he got the Y from Dad. This mom, she is not colorblind, so one of her X chromosomes has the big B, but she produced a son with colorblindness. So he had to get this little B from Mom. Remember, he can't get it from Dad. 1, because Dad doesn't have that to give him, and 2, because he already got the Y from Dad. So that means that Mom is a heterozygous female. When we talk about sex-linked trait, we call heterozygous females we call them carriers. Carriers because they carry the allele, but they don't express it. Sometimes on pedigrees, they'll be filled in halfway, because this is like the big B side and this is the little b side. So sometimes they're filled in halfway, sometimes they're not. Even without filling her in halfway, I know that she has to have at least one of the little b alleles because she passed it on to her son who has colorblindness. Now, both of these daughters do not have colorblindness, which means that they have an X chromosome with a big B on it. But we don't know if that came from Mom or from Dad. So their second allele could be big B, or could be big B, little b, where we're not sure. Let's say that this female, though, she had offspring with another person. Let's say that she had kids with a male who is not colorblind, and they produced 4 daughters. Oops. Pretend that's a circle. And none of those daughters are colorblind, and one of those daughters marries, or maybe doesn't marry, but has children with another male, and they produce kids, and of those kids they have 2 boys. I'm just making up a family story here. And one of those boys is colorblind. Now we can kind of carry things back and figure out what her genotype is based on this. So this boy, we know his genotype. He's got a little b and a y. He got that y from this male here. This male is not colorblind, so he's big BY. His brother is not colorblind, so he's big BY. That means that Mom has to be a carrier. Mom is not colorblind, so she's got one big B, but she had a child with colorblindness, so she is a carrier of that gene. Let's look at this lady and go back to her parents. So her dad was not colorblind. And since he has this, genotype. The only thing he could have passed on to this person here is the big B. That means that this little b had to come from her mother. So now I've just figured out her genotype based on her grandkids, because these are her children and these are her children's children. So things to note. This can skip generations. That's exciting. And just like in a recessive trait, if two parents don't have the trait, that doesn't mean that their kid will not also. So parents without the trait can produce kids with it. And the last thing to note, and this is the big giveaway, X-linked traits, they affect males more than females. Of this whole, what is this, 1, 2, 3, 4 generations in this family, it was only boys that got colorblindness. Let's look at that a little bit more. So let's imagine that I have 3 situations. I have a mother who is a carrier, and I have a father who is not colorblind. That was the case in most of our Punnett square above. In that situation, I will produce daughters, and based on this Punnett square, 0% of my daughters will ever be colorblind. If I look at my sons, 50% of my sons will be colorblind. So let's do it again, but now let's look at a female, a mother who is colorblind, and a dad who is not colorblind. So here I have this daughter, she's not colorblind. Same thing, she's not colorblind. And now 100% of my sons are colorblind, and 0% of my daughters are colorblind. So the males are affected more because they only have one shot at getting a dominant or recessive allele for this trait. So can I ever end up with daughters that are colorblind? And the answer is yes, but to do that, I have to have, let's say mom is a carrier, and dad is colorblind. Now I have one daughter who is not colorblind, one daughter who is colorblind, and then a son who is not, and a son who is. So now it's 50% of both, regardless of the sex of my children, are going to be colorblind. But to do that, I had to have a colorblind dad. So as long as my dad was not colorblind, he passed on this big B to his daughters, and none of my daughters were going to be colorblind. All right, thanks for joining me. Please email me with questions, and I look forward to chatting more about pedigrees. Have a great day.